All right, we begin chapter 4 today, which is about integrals and integration, right? You can see these phrases here. Maybe new for you. Integration is the process of finding an antiderivative. Okay, so this is algebraic in nature, right? This process where we started sketching antiderivatives last week, right? Now we are actually finding the formal functions that pair with the antiderivative. So an integral looks like this. You can see this little symbol here, right? That's an integral symbol. It's just a long skinny S. Think of like a candy cane on both ends or whatever. Eventually I will explain why it's a long skinny S, but for right now, we just have to think about what it means mathematically. So this question right here says to integrate 2x, just the function 2x. dx is a notation that we'll, again, talk about later on. It's tied to the whole dy dx thing that we've been using for derivatives. But what an integral does is it asks this question right here. It says integration says if a function is 2x, then capital F of x is what function, right? So there's a function out there, right, that when you take its derivative, you get 2x. The question is, what is that function? So I want you to type that in to the question. But here's the catch, right? There's more than one function, right? Can you think of another function that has the same derivative as x squared? Right? That's the catch, right? That x squared plus 3, that function's derivative is 2x. X squared minus 2, that function's derivative is 2x. We've got x squared plus pi. That function's derivative is 2x. And we have a whole series of functions that all have the same derivative. Okay, this ties back to the graphs that we were sketching earlier, the antiderivatives. They can be situated anywhere vertically, right? Because we have that translational number at the end is what moves the antiderivative sketch up or down, and it can be located anywhere. So that's exactly it. So the answer to this question over here originally looks like this. We say the answer to the integral of 2x dx equals x squared plus c. Okay, that c represents the constant that could be any number because they all come down to the same derivative. Okay, so looking at this notation here, you see this integral symbol right there. Okay, it is just a long, skinny S. So think of it like, right, a candy cane on both ends, like I said. And this function here, that's in here, this is called the integrand. So like radicals have radicands, integrals have integrands. And then the dx is what we call the differential. It doesn't have any meaning yet. After we get through a couple sections in chapter 4, we'll reveal its meaning. So stay on the edge of your seat. And then, like I said, f of x itself is called the integral, meaning we call that the integral, like it's the function that is the antiderivative. And then sometimes we call it the antiderivative. So those two words can be interchanged. And then the plus c has a very proper name. This is the constant of integration. Gration. So if I had a super dope echo feature, I would use it, but I don't. So that constant of integration goes in every integral that we calculate. All right. So we have to kind of systematize how we come up with antiderivatives, right? And there's really only one rule that's going to get us through a bunch of different chapters, or a bunch of different sections in chapter 4 here, and that's the power rule for integration. It's literally the reverse of the power rule for differentiation, okay? So what it says is that if you have the x variable raised to any power, right? Like thinking about x squared down here, like example 1. What it says is to add 1 to the power, so x squared becomes x to the third, and then it says to divide by that same number, okay? So remember when I asked you the question, the integral of x squared, that's a very different question than the integral of 2x. So we apply the power rule, and then we tack plus c on the end. So that's how integration works. We just found our first answer. So again, highlighting here, the only thing that changes, bing, is the power and then the denominator. Okay. What else was I going to recommend? Because it's a power rule, just like all the other power rules, when it comes time to integrate something, we definitely have to write it in a power format in order to be able to integrate it. So like in example 2, right away, I'm going to rewrite this before I integrate this as 2x to the 1/2 power instead of root x, because that power format is the one that's going to help me to integrate it. So again, my next step, as soon as I integrate, meaning as soon as I apply the power rule, I am going to not write the integral or the dx any longer. Okay, so my work is going to look like this: 2x to the 1/2, and then if I apply the power rule, I have to add 1 here, and then I have to divide by 1/2 plus 1. You'll start doing that part in your head, but just for the first step, I want you to kind of see how that looks. So now we calculate that. So that's 2x to the 3/2, right? If I have to add 1 to it, I do it with common denominators. And then 1/2 plus 1 is also 3/2. So dividing by a fraction, is the same as multiplying by its reciprocal, right? So dividing by 3/2 becomes multiplying by 2/3. And then we have times this 2 that was in the original problem, x to the 3/2, and then plus c. So I'm going to clean this up so it ain't so ugly. So that's 4/3 x to the 3/2 plus c. I will tell you that the AP people are psychotic about this power being vertical, right? They don't want you to use a slanty fraction. So that's not my request. That is straight from them. So please try to use the vertical powers to do that. Okay, so let's do a couple more together, pretty quick-ish here. I'm going to rewrite example 3 as 3x to the -4. So when I rewrite it, I keep the integral and the dx, and now I'm going to apply the power rule. So now I'm going to drop the integral and the dx. So notation-wise, it's very important that we get this part right. So 3x, if I add 1 to -4, I get -3, and then that new power is what I divide by. Okay, canceling those out. Think about how this simplifies. My negative remains. So I'm going to rewrite this as -1 over x to the positive 3rd power. Oops, what is that? Not dx, plus c. Okay, so take a minute if you need to kind of think about how this and this, right, turn into the non-power version, right? Writing it rationally in example 3. Examples 4, 5, and 6, I'm just jamming in here at the bottom because they are pretty quick, almost, I don't know, theorems is too strong a word, but it's just the simplest cases of integration. So if you're asked to integrate the number 0, right, the antiderivative of 0, since it's 0, it would have to be a constant, right? So that antiderivative is just the constant of integration, c. Okay, example 5, when it just says integral of dx and there's nothing in the integrand space, your brain has to interpret this as the integral of 1 dx. So you're actually integrating the number 1. So you can think of that like 1 times x to the 0 power, right? Because that's still equal to 1. So you have to increase that degree on x to a 1. Dividing by 1 doesn't change anything from the power rule. So if this is what you're integrating, you actually just end up with x plus c. Okay, so the integral of 1 is x, and then plus c is the constant of integration. So anytime you have a constant here, whether it's a 1 or a 3 or a 5 or a -2, technically, right, we're just attaching the x to it, and then adding the constant of integration. So those will come up from time to time. Okay, a couple special formats here. In example 7, we have a binomial squared. So you have to think of this as a function being raised to the second power, right? Which we don't have a rule for, all right? We have a rule for if we have a single variable x being raised to a power, all right? So when you see something like this, we actually have to transform this integrand into a series of powers by actually squaring this out, right? So that's going to be 9x squared plus 12x plus 4 dx. Okay, so notice when I'm rewriting it in a different format, I am just keeping the integral in the dx. Now my next part is where I'm actually going to integrate it, and that's where I will drop the integral in the dx and then include my plus c. So I'm going to just do it like one term at a time. Okay, come up with each antiderivative. So the antiderivative of 9x squared is 9x to the third over 3. We'll simplify it later. Plus 12x squared over 2 plus 4x, which we just picked up in the last example, and then the constant of integration. So canceling things out, this is 3x cubed plus 6x squared plus 4x plus c. The end. Okay. All right. Example 8 is a little difficult. Not too difficult, but it works your brain a little bit. You'll notice here we have a single power of x in the denominator. Okay, that's when you know to do the next step. When we have a single power of x, we're going to actually divide each term by it. Okay, so since I'm still simplifying, I'm writing my integral and my dx. I'm now going to simplify, right, my powers using the rules of exponents. So I'm just rewriting everything as a power right now. Now I'm going to simplify those by subtracting, right? The first one, the 1 minus the 1/2 is x to the 1/2. And then the second one can just be written as x to the negative 1/2. Okay, so I haven't actually integrated anything yet. It was a series of simplifications. So my integral and my dx still exist. So now I don't write those any longer when I go to actually integrate. So now let's do the first one, right? X to the 1/2 becomes x to the 3/2. And again, it's divided by 3/2, which in turn makes better sense to write as multiplying by 2/3. The next one is x to the 1/2. So again, when you integrate that, you have to do negative 1/2 plus 1, which is positive 1/2. And then again, I have to divide by 1/2, but that's a bit awkward, so I'm just going to multiply by 2, following those rules, and then put a plus c. And this is my answer. Okay, you might be asked to put it in a radical format, but you should be able to transition easily between radicals and their powers and vice versa. Okay. Ooh, the next one is the integral of cosine. So again, what function is it that you differentiate and get cosine? Right? That's the sine function. Right? So this one is sine of x plus c. That's it. We can apply those same old trig derivatives in reverse. So this box here is a series of the 6 trig integrals that you know. Okay, you guys notice that tangent, you don't know how to integrate tangent. We won't learn that until later in chapter 5. Okay, so for right now in chapter 4, only the 6 derivatives that we had in unit 2 are able to be integrated now in chapter 4. So the integral of cosine is sine of x. Okay, integral of sine of x is negative cosine. Got a really great memory tool for this one. You ready? Thought about this for years, came up with it. When you integrate sine x, change the sign. Ba-dum-bum! Right? So you'll notice it's going to be hard to keep track of when you throw negatives or make it positive or whatever, the more we like go back and forth between derivatives and integrals. So when you integrate sine, change the sign. Okay? Keep going. Integral of secant squared is tangent of x plus c. Integral of cosecant cotangent is negative cosecant x plus c. Integral of secant x tangent x is secant x plus c. And the integral of cosecant squared x is negative cotangent x plus c. You'll notice that all of the answers that have a co in them, right? The cosine, the cosecant, the cotangent that I've highlighted, all of those co-trig functions are the ones that change signs. So I know it says negative here, but remember that if the integrand comes with a negative in it, then you have to change the sign and make the antiderivative positive. So that negative needs to be interpreted as just an opposite sign, okay? So this box is really good to try to work on memorizing, like write it out 10 times in a row, 5 times in a row, so that you can start to think about these in reverse, okay? So 10 and 11 take us through just a couple integrals. Again, I'm going to do this each one at a time. So the integral of 3, right, is going to be 3x. And then the next integral is minus sine x. So you'll notice right up here, when I integrate sine, I change the sign. So I'm going to write plus cosine x plus c. That's my answer for number 10. Okay, see if you can do number 11 on your own. All right, so you should get x squared over 2 for the first term, and then integrating cosecant squared, it does change signs, so this would become plus cotangent x plus c. Hopefully you did well. All right, last little bit of information here is what we call differential equations, and we're doing the simple kind today, the kind that are only based off of x only. Okay. Of x. So we introduced this a very little bit in one of those note sheets a couple weeks ago about this phrase differential equation. Okay, so the simple kind are based off of x. The more difficult kind get their own chapter in chapter 6, and those are based off of x and y. Okay, so that's what makes those more interesting. The cool kids call differential equations diffie-q. Okay, so if you're going to walk around campus with your coffee in your hand, you're going to call it diffie-q. And in college, there's an entire course devoted just to solving differential equations. So it's an important calculus topic. So we're just setting a basis for it today. So the answer to a differential equation is a function. Okay, so it's not a number, right? A lot of students get caught up, oh, it's an equation that I have to solve, it must be a number. No, the answer is a function. So it's a different sort of equation than we've solved at any other time. So example 12 here is our first case. It says find the general solution of the differential equation. So what this looks like is it just looks like a derivative, right? dy dx equals secant squared, okay? Very true. Notationally, it does look like a derivative, but the directions tell you to do something different with it. So what we're going to do is we're going to take this equation, right, and we are going to integrate both sides. So when I integrate here and integrate here, I'm going to get y, right? Because the antiderivative of dy dx would be the function y that it came from. And then the integral of secant squared, right, if we check up here, right, is obviously tangent x. So this is going to be tangent x plus c. So all this particular question asks us to do is integrate both sides. So a general solution is this equation here that says y equals tangent x plus c. So it's an actual function, right? If you just put tan x plus c, technically you're wrong because it doesn't say y equals. I know it's a minor detail, but it is pretty hefty to understand why it's y equals, in the big scheme of things. Okay. So a general solution is when we have plus C on the end. I'm going to have you try example 13 here and type in your result. See if you can find that general solution. Okay. Just use the caret whenever you need powers. And then example 14, which is our last of the day, changes the phrase a little bit. This says to find a particular solution. So that changes the game up a little bit. We still have a differential equation given to us, dy dx equals 2 times x minus 1, but it gives us a point that that equation passes through, and here's how we make use of that point. We're going to integrate the left side. In order to integrate, I'm actually going to make the right side 2x minus 2, and I'm going to integrate that as well. Okay, so integrating the left side just gives us y equals, and integrating the right side gives us 2x squared over 2, applying the power rule, minus 2x, and then plus c. Okay, I can cancel those. So my general solution is y equals x squared minus 2x plus c. But now I have a particular solution where I'm going to take 3, 2, and I'm going to plug that in. So 2 goes in for y. 3 goes in for x, and I'm going to solve for c. So 2 equals 9 minus 6 plus c, 2 equals 3 plus c. Looks like negative 1 equals c. And again, my particular solution is not negative 1. My actual answer is y equals, I go back up to my general solution, right, this step, and I put the c in its spot. So this is my particular solution. So you can kind of just see the difference in what a general solution looks like versus a particular solution.